Okay, ladies, so we're going to look at a basic scenario of projectile motion. So here we have a car traveling 20 meters per second, heading towards a cliff, I guess, and the cliff is 100 meters high. We want to know how far does the car travel horizontally, okay? So what that means is we want to know this direction. How far does the car travel in this direction? We know that the car is going to, if you were to trace out like the path of the car, we know it will be something like this, right? But we already know how far it's going to fall vertically because we're told the cliff is 100 meters high, right? So we know it's going to fall 100 meters. But we want to know how far does it travel horizontally? Well, we're going to have to answer a very simple question. How long does it stay in the air for? So we're going to first figure out how much time does this car stay in the air. So how would you solve a question like that? How long does this car stay in the air? Well, let me ask you a question. Something going off a ledge horizontally and something being dropped, do they reach the ground at the same time? They do. We already examined that scenario, right? An object falling and an object moving horizontally off something hits the ground at the same time. Because if I was to say to you, what's the initial speed down? As the car is off the cliff, what's that initial vertical speed down? What would the answer be? 0. So the initial speed in that y direction is 0. So now, this is the same as something being dropped. So how do you figure out how long it takes for something to be dropped? Well, we could use this equation. Right? That's the equation we could use for something with no initial speed and has an acceleration, and we know exactly how far it's going to travel. We could solve for time using d equals half at squared. And then we know we could rearrange that to figure out time. So time would be 2d over a. Okay? So how long does it take to fall? So that would be 2 times 100, but it's 100 meters down, so it's going to be negative 100 over negative 9.8. So it's about square root of 20, very close to square root of 20. So, but what exactly is the answer? 4.5? Okay, 4.5 seconds. Now, yes? Because it's initially traveling, if you think of its speed, so it's on a ledge, if you had to visualize it as a vector, it would be pointing this way, right? It would be 100 meters per second to the right. But does it look like it's pointing down right now? No. So whenever we talked about vectors, and we can take a vector, we can break it down into its components, right? So this vector here that I just drew looks like it's moving, looks like it's pointing right, but it's pointing up. So this would have a horizontal and a vertical component, right? This vector only has a vertical component, but this vector only has a horizontal component. Its vertical component would be in fact 0. So this car has a horizontal component of 100 meters per second right, but a vertical component of 0. Remember, the big idea is consider the x and y independently. Sorry, 20 meters per second. Yes, 20 meters per second, not 100. 20 meters per second. So its initial speed down is 0, but its speed to the right is 20 meters per second. So we know now that it takes 4.5 seconds to hit the ground. Now, what's happening in that 4.5 seconds? Yeah, it is falling. And yeah, I heard it. It's also traveling this way. Now, if you were to think about the speed along the y direction versus time, if I was to graph it, would the speed be increasing in a negative direction, or would it be decreasing? It would be increasing, right? So if this is 0, we know that the speed would be increasing in a negative direction, right? Because of what? Gravity. But if we were to consider the horizontal speed over time, that would remain actually constant. And that's because the horizontal speed and gravity are perpendicular to each other. So in other words, gravity does not affect the horizontal speed. It's the exact same scenario as you have a swimmer who is traveling this way and the current is traveling perpendicular to the swimmer. Does that current affect this component? The answer is no. We know that the swimmer ends up going on an angle, but this component is still the same. So if you want to know how far this cart traveled horizontally, it would be a function of the horizontal speed, which remains constant in a projectile, times the time. Now, when I say remains constant, because we are ignoring the one thing that would affect the horizontal speed, which is friction. And that would slow down the horizontal speed. I mean, if you watch like a football game or you'll see the soccer ball going in a projectile motion, but you'll notice that it does kind of slow down a little bit because of friction. But, we're going to make things simple. So how far does it travel? So it's going to be the horizontal speed, which is 20 meters per second, times the time in the air, which is 4.5. That ends up being 90 meters. So it should be 90 meters from the cliff. But in reality, if there's a little bit, but you would imagine that, it probably would be very close to 90. Yeah. Now, and of course, that all depends on the object, right? If we were throwing a piece of paper over the cliff, then friction would have a significant impact. Sorry, what was the question? Yeah. Right. No, the currents, remember the X and Y are independent, right? So the current and the example with the swimmer, those are independent of one another. You end up swimming at an angle, but if I was to ask you a question about how long does the swimmer take to move vertically, that vertical component is constant. Yeah, it's constant. However, the swimmer does travel at an angle, right? Just like this car. This car is not traveling just down. It's not traveling just across. It's traveling down and across. But the question is just simply, how far horizontally do we travel? So we just need to consider the horizontal component for the speed. Okay? So let's look at the next question, and then I'll pause it. All right, we're going to do a range and max height, but I have another question. Let me pause this video. Okay, so here's the second scenario. We're going to look at range and height. So remember, range is another way for saying distance along the x, and height is another way of saying the vertical distance. Okay? Let's not complicate stuff, Anissa. All right? Shh, quiet. So we're going to figure out how high it goes, and we're going to figure out how far it goes. I'm going to, and this scenario here is a projectile that is fired from a particular location, and it ends up traveling. Basically, if you think of this line here, it ends up with no vertical displacement. Now, what I mean by that is, imagine that you have a ball in your hand, you throw it up in the air, and it basically lands in the exact same spot vertically from where it left. Because the scenario I'm going to show you tomorrow, we'll look at a different one where maybe the projectile starts off here and ends up somewhere down here. Okay? Whereas this, it starts off here It goes up, it comes back, but there is no vertical displacement at the end. Okay? But then tomorrow we'll look at a more complicated scenario. But, start with the simple stuff. So I'm going to ask you a really simple question. Do you remember this scenario where object just goes straight up in the air? Okay. So we can figure out how long it takes to go up. And if you had to figure how long it takes to go up, what equation would you use? So we're going to do the height first. Okay? We're going to look at the height. If I wanted to know how long something takes to go up, right? What equation could I use? Time to go up. What equation could I use? Well, if I look at this vector, I'll notice it's pointing up, but it's also pointing to the right. Okay? So I can see that it has a vertical and a horizontal component, right? But if I want to know how long it takes to go up, what three things do I need to know? Well, I need to know VF, I need to know VI, and I need to know A. Because I know at the top, the vertical speed is what? 0. So really, this just simply becomes negative VI over A, because VF is what? 0. But the question is, what's VI? Well, if I look at this project, this is a little bit different than the ledge question, right? Because in the ledge question, I only had initially a horizontal speed. But here I don't. Here I have a horizontal and a vertical speed. The vertical speed is a function of, well, it's the opposite side. So that would be a function of sine 45 times 100, right? So when we looked at examples of relative motion and two-dimensional motion, we had to look at the components, the x and the y. So in this case, we need the components. So the vertical component is the opposite side. The horizontal component is the adjacent side. Now, if it's cosine 45, sine 45, it's exactly the same thing. So the components are the same, 71 and 71. So what's my initial speed up? 71. Exactly. So that's what's meant by upwards velocity. Whereas in the previous example, what was the initial vertical speed? 0. Because the vector was only pointing horizontally. That's right? So that's the actual velocity of the projectile. But what we could do is we can break it down into its components. You know how we did with the component method? We have the XY chart. That's what we got to do here. So that's the actual speed of the projectile. But what we can do is we can consider, okay, what's the horizontal component and what's the vertical component at this moment in time? Okay? So at this moment in time, the horizontal component is 71 to the right. I'm going to say to the right. And 71 up. So if I want to know how long it takes to go up, it's a function of this equation. So the time up is negative VI over A. But A is, what's A? Negative 9.8. So the time to go up is, what is that, like 7.2 seconds? I'm going to work it out. Okay, I'll just say 7.2 seconds. All right, now, okay. How far does it go up? Well, we can now say, well, the distance up would be a function of the average speed up along the y times that time to go up. Just like the example we did on the test, right? Object being thrown in the air. So the average speed up is the average of 71 and what? 0. Because at the top, what's the speed? 0. How long does it take to go up? 7.2 seconds. Alright, so what's that distance up? So it's the average of 71 and 0 is 35.5 times 7.2. So what exactly is that? $256 meters. So this is 256 meters up. Okay, so that's the max height. Okay, so the max height of a projectile is when you get to the top of the curve where the vertical component is 0. Because if there's still a vertical component that's positive, that means it's still going up. But if the vertical component is 0, that means you've got to the top. If the vertical component is negative, though, that means the projectile is coming down. Alright, so how do we do range now? Now, because this is perfectly symmetrical, I want you to think about how long does this projectile take to go up and come down. Rapti? Double the time. So, 7.2 seconds to go up and 7.2 seconds to go down. The total time this projectile is in the air is about 14.4 seconds. Okay? As long as it's in the air, what's this projectile doing? It's moving to the right. How fast is it moving to the right, though? Well, this does not change, right? Because we said that we're going to ignore friction. So if you want to know what the range is a function of the horizontal component. So that would be the horizontal speed times the total time in the air. Okay? So I put TT to remind me it's total time in the air, not just the time up. So that would be 71 times 14.4. Notice I'm not using average speed because it's not changing. It's constant. So that should be very close to 1,000. 1,022? Oh, wait, 1,024? Okay, 22. So 1,022. I guess I'm just going to say to the right. Now, tomorrow, I'm going to stop here, but I'm going to ask you to consider, do you think if the projectile landed here, maybe somewhere, do you think the times would be do you think they would be perfectly symmetrical? Time to go up, time to go down? No. So in this scenario, when it is perfectly symmetrical, it's a perfectly symmetrical problem where you can slice it right in half, then yeah, time to go up, time to go down is the same. Tomorrow we'll look at what if they're not the same. Okay? So I'm going to stop here. This is just part 1.